All right, guys, let's finish this up. So when you're given a graph, just make sure you know what graph you're looking at. So we are looking at the graph of the derivative, f prime. So when is the original function f increasing? Well, it's increasing when the derivative is positive, so it'll be above the x-axis. So from here to here and from here to here. Okay, so it would be increasing from, or let's see, we'll say on negative infinity up to that x value a, and then also from b to c. And you want to reference whatever graph you're looking at. So we're looking at the derivative. So the derivative is greater than 0. At what values does it have a local max or a local min? Okay, so it's going to change from increasing to decreasing at a, and also at C. So those will become, let's see, increasing to decreasing. Told you guys I always sketched out. That would be a maximum. So local max at x equals A and C, because the derivative changes from negative to positive. Likewise at B, it's changing from decreasing to increasing. So, this should be positive to negative. So that means we have a local max at x equals B, because f prime of x changes from negative to positive. And then we need to state the inflection points, okay? So the inflection points would be where the second derivative equals 0, right? And that would be where, let's see here, where we have these horizontal tangents at the maxes and mins of our derivative, because then the derivative of that derivative will be equal to 0. Also, you can see that the derivative is changing from, let's see, decreasing here, and then it starts increasing, and then it goes back to decreasing. Okay, so we would say at x equals -1, or sorry, I guess point, so it's -1, -3, and 3, 2, and we're going to justify based on what we have. We have f prime, so because f prime of x changes from decreasing to increasing, or increasing to decreasing. I'm not mentioning the second derivative because that's not what I have. I have the first derivative, so that's my justification. So on what intervals is the function concave up or concave down? Okay. So it's going to be concave up when the second derivative is greater than 0 or positive, which means that the first derivative is increasing. So we know that the derivative is increasing from -1 to 3. So it'll be concave up. Because f prime of x is increasing, which means it'll be concave down from negative infinity to -1, and from 3 to infinity, because we are decreasing. Our derivative is decreasing. So we can tell a lot from that first derivative graph. So a lot of times we're given that first derivative graph, because we can even look at the derivative of that to determine the second derivative for concavity, and then also look and think about the original. Assume that f of 0 equals 0. Can you sketch the graph of f of x? So we know, okay, we have 1 point. We know we have a local max at A and C. So we'll put those in. So we had A, B, C. So I'm going to kind of make those maximums. And we had a, oh, and you know what? I just noticed the typo. Local min at B. So I'll put B lower. So that means it's going increasing, and then it's decreasing, and then it's increasing. And I didn't check, where do we change concavity? At -1, -3. And actually, we don't know the y value, because that's the y value I stole. Sorry guys, I messed up. So we just need to know the x value. So x equals -1 and 3. So here we'll say this will be -1. So that we want that to be our point of inflection. So I'm going to change this part of the graph. So here we're concave down. Then it switches to concave up. And then it's going to go concave down again at 3. So we'll put here. So concave up, and then switching concavity again. Okay. So you can see that if I look back, I switched concavity here. I went from concave down to concave up, switched it again at 3, so concave up, and then all the way concave down. And I kept my maxes and mins in there, so there's my sketch. We do more sketching in the next lesson. All right, last example. In the table to the right, selected values of G, G prime and G double prime are shown. We are given it's twice differentiable, so continuity is implied from -4 to 5. So explain why there must be a value between -4 and 5 such that G of C equals 7. So I know that, let's see, G of -4 is 0 and G of 5 equals 8. So since G of X is differentiable and therefore continuous, and so that 7 falls between G of 4 and G of 5, then let's see. Oh, you know what? I mixed up therefore. That's our symbol for therefore. And therefore continuous. Then there exists a value C on the interval -4 to 5 such that G of C equals 7. So we used our intermediate value theorem, our IVT, here. And we needed continuity, and we were given differentiability, so we needed to state that since it gave us differentiability, therefore it's continuous. All right, explain why there must be a value D such that the derivative of D is 8/9. So I'm seeing, okay, there must be a value. It's probably one of my VTs. Talking about the derivative, so I'm going to use the mean value theorem. Okay. You could also, well, let's go that way first. So we know that G of -4 equals 0, G of 5 equals 8. So if we do G of 5 minus G of -4 over 5 minus -4, that's going to be 8 minus 0 over 9. So that's going to be 8/9. So since, let's see, G of X is differentiable and therefore continuous, there exists a value D such that G prime of D equals, oh, on our interval, you got to state your interval, is equal to our average rate of change, which in this case is 8/9. In this particular example, because you were given that it's twice differentiable, if you wanted to use the IVT and say that 8/9 falls between -6 and 3, and you know that that derivative is continuous since it tells us it's twice differentiable, you could also use the IVT talking about G prime. So it would look a lot more similar to A. But here, I think what they wanted us to do is use the MVT, especially because it equals 8/9 when I take that average rate of change. So does G of X have a local max, local min, or neither at X equals 3? Okay, so I know at X equals 3, it's a critical value because the derivative equals 0. And then I know that the second derivative is negative, so it's concave down at that point. Okay. So we know that, okay, if something's a concave down, it's going to create a maximum. So we could say local max because G prime of 3 is equal to 0 and G double prime of 3 is less than 0. Can concavity of G of X be determined on the interval -4 to 5? Why not? And I would say no, because we don't know if there's any other, we don't know the in-between values. We're only given 3 values. We don't know if other critical values exist. Okay, it's only just giving us selected values. Yeah, I'll just leave it at that. We don't know. So not enough information. So basically we know this is a nice table and we're going to talk more about it next time. But when the first derivative equals 0, we're going to have critical values. And then if the second derivative is greater than 0, it's relative minimum because it's concave up, relative max are concave down. And then you can see where it's increasing concave up, decreasing concave down. And because next time we go on to curve sketching, yay, so we put it all together, which is why I wanted you guys to make sure you finish this before. So I will see you on Thursday.